uncomfortable questions to the speaker and test them on what they were telling you now. So I'm going to give you guys these seats, so it'll probably be just a little bit easier.
Okay. Thank you.
And just to remind everybody, we do have a Google Doc available for everybody to send their questions through. It's right up here, jonthebeach.com/Gromenauer-doc. There we go. Thanks. Perfect. So we already have a few questions, so we'll get started off with those. And if you guys have anything else, please send them in on through the Google Doc. All right, so I think this first question is for you, Zoltán, is how did you measure and compare the complexity of writing applications for FPGAs versus CPUs?
I presumed whoever asked the question refers to one of the slides with the bar charts. What I wanted to kind of give you an idea about with that is what kind of programming constructs or you can use on these different devices, or how flexible the programming models are. So basically, if you are writing code, how many things you can do in that code. And on CPU, you can do, as mentioned, pretty much anything. On GPU, for example, you can't use every data construct, the data structure, every language construct that would be in C++, for example. And with FPGAs, using such high-level tools, in my experience, is kind of in between. And that's certainly the case with Hasslier. That wasn't a very numeric result, I would say, just to give you an idea.
All right, and then when we're looking at CPUs versus GPUs, would you say that they have the same power efficiency?
I would say that generally it highly depends on the specific use case. I would say that there is no clear winner here. So for certain use cases, CPUs can be more power efficient. For certain use cases, GPUs, and for certain use cases, FPGAs. So it's not a silver bullet with FPGAs. But for each of these devices, you need specific workloads. FPGAs are just another tool.
Okay, so I'm going to jump to a question for Benedek, just to switch it up a bit. I have one here, and it says, what kind of apps could benefit from using alternative number formats?
Mm-hmm.
I think you touched on that a little bit.
Yes, so basically I would say almost all of it, but in some cases you might have constraints that don't really allow you to switch out the number formats that you're using. So if you need to maintain compatibility with the legacy system, you might be in trouble. But if you are developing some algorithm, or maybe using an algorithm on a specific set of servers for a couple of months, and you are actually developing this algorithm now, it's definitely worth trying. So almost everything where you need to do serious number crunching, or even not so serious number crunching. So it's even if it's just some random calculation, it might be worth a try. But like I said, the benefit here is that you can actually use less bits, and even then you can actually gain higher precision. So I think those are pretty huge selling point in any case. And yeah, data centers actually have power problems nowadays. So it's not about the hardware; it's about how much heat you are wasting, basically.
Okay. All right, and then another question here is, how long does it take to compile a program for an FPGA?
Mm-hmm. There are basically two steps here. First, there is the kind of compilation, we call it transformation of Hasslier. So I haven't shown that, but Hasslier generates so-called VHDL code, so hardware description language, hardware code. That takes at most a few minutes. And once that is done, then we feed that hardware code to the FPGA manufacturer's own tool chain. And then comes what is called the bit stream generation, and then the configuration of the FPGA. Now, this is quite hefty. So depending on the complexity of the design, this can take half an hour, 1.5 hours. But you only have to do that once. So after that, you can execute it as many times as you wish.
Okay, and then kind of going off of that, there's another question here, which is, what are the most expensive operations for an FPGA in terms of hardware resources needed?
That would be actually, I think, floating point division, probably from the usual operations. So actually, our recommendation would be that if you are using Haslier or FPGAs in general, if you can live without floating points, do that. Use fixed point or integers. We also have a fixed point number type supported by Haslier. But if you need floating point, then at least try posits. Because posits, it seems we are still in the process, and the whole community of posits researchers and developers are in the process of evaluating it, but POSIT seems to be more hardware friendly.
All right. So I'm going to go off a couple of more here, and then I might open it up just so that we can get some, I know there's probably some questions that are stemming off of some of the answers that Benedek and Zoltán are giving. So I have a couple of questions that just came up, and it's, we may be going back to some of the answers that you gave out previously. It says, so you mentioned that Python is supported. Is it Python 2 or 3?
It's actually Iron Python. So,
can you repeat that?
It's actually Iron Python.
Iron Python.
Yes,
okay.
I think that's a subset of Python 2. So we are only supporting .NET, just to make clear, and all .NET languages that can be compiled into the .NET bytecode are which we support. So in case of Python, that means the Iron Python implementation. Yeah, no, that's in short.
Okay, and then the second question below that one, so I think it might be the same person. It says, would it be possible to implement, would it be possible to implement an interpreter, for example, Java VM, in the FPGA hardware to use, to run the bytecode in it?
Well, that's a quite interesting question. And I think somebody already did, or at least try to create a Java machine, so not a virtual machine, but an actual Java machine. The short answer is that with Haslier, we are shooting for something else. So we are targeting .NET and .NET languages. But you could basically create a Haslier for Java as well. What we do with Haslier is not that we create a .NET runtime on the FPGA, but we directly transform into a hardware implementation what you have as a logic in C#. So you could do the same thing with Java, or you can even do, I would presume, a Java machine on an FPGA. I would check out what they have done there. Any follow-up?
Just to add to that, I come from a company that used to do special hardware, especially to run Java virtual machines. That's what Azul is known originally for. About 6 years ago, we gave up on that and switched completely to Intel, both because of cost of manufacturing custom CPUs, and also because Intel by that time implemented all the ideas that the company had by that time. That would seem more beneficial to, previously seemed more beneficial to implement in hardware. So commercially wise, I think for JVMs it's better to go with conventional CPUs. That said, perhaps FPGAs can be a good way to test some ideas. For example, transactional memory. Things of that nature, which are experimental, and to run that experiment on something like x86, it will take them years to just do something like that. Meanwhile, you can do a prototype, build a prototype, show it's profitable, and then maybe one of the major vendors, ARM or Intel, will pick up that idea.
Yeah, indeed, that touches on an interesting idea, because how we use FPGAs here is like an accelerator card. But how traditionally FPGAs are used are as a hardware, I would say probably simulation board. So indeed, you could implement your own kind of memory and implement it and test it on an FPGA as an actual piece of hardware. And even if that works, after some further steps and a couple of millions of dollars, you could actually build that piece of memory as a piece of hardware as well.
Does that answer the question? So maybe taking it on a higher level, there's a couple of questions here with regards to adoption of FPGA. So what do you think has been a blocker at this point for adoption?
I think two things, because FPGAs are still kind of a curiosity, I would say, although they are becoming more mainstream. But two things, I think. First of all, the development experience. So there are multiple orders of magnitude fewer hardware engineers than software engineers, and there's a reason for that. And secondly, to use an FPGA, you had to purchase an FPGA, which in the case of such a board, it's just $300, but in case of a more serious board, it's $10,000. So that's not something everybody would do. Now there are, to mitigate these two issues, we have some solutions. For the development experience, there are tools like Hestia. There are other high-level tools as well. If you are coming from the FPGA side, it's called high-level synthesis tools. And secondly, as for the acquisition of an FPGA or to get access to an FPGA, there are cloud FPGAs nowadays. So,
sorry, did you say there were cloud?
Cloud FPGAs.
Okay, that's actually the next question, so that's perfect. Yeah.
Oh yeah, so two cloud providers Benedek already mentioned were AWS. I think they added FPGAs by the end of 2016, and they were widely available in the beginning of 2017 or so. And they were, I think, the first big providers. So we are quite in the beginning, but at least it has started.
Okay, and then I think you touched on this a little bit earlier, but maybe we can go back to it. It's whether you use OpenCL to program FPGAs, or would you do that?
We don't use that. That's another technology with a similar aim. So, with OpenCL, you also have kind of a multi-platform programming model that you can use to target multiple kinds of devices, including certain FPGAs. We are going a different route. It's a bit similar in this way to OpenCL, but the programming model is different. So our ultimate goal is that you take any basically suitable .NET program and can convert it into a hardware implementation. We are not there yet. There are multiple limitations that you have to work around, but we are starting from the development experience standpoint, that you are a software developer, possibly a C# developer, and we want to get rid of any limitations that you may have for FPGAs. You don't have to learn a new programming model like with OpenCL.
Okay, so we're actually on time right now. I have a bunch of more questions here for you guys, but I think I'm going to leave it up to people to come up to you and bombard you with questions during the break. So unless there's like a pressing question in the audience, I'm going to close out the session. And with that, I really want to thank Zoltán and Benedek for joining us today. You guys came all the way from Hungary, which is a bit of a travel. I've been there, and I know there's a lot of layovers. So if we can give them all a round of applause. Thank you very much on behalf of the organization.
Thank you.
Thank you.